Hello, this is Jack Jackson. We're back with 5 more exercises from our review exercises for Unit 2B. As before, I'll show you an exercise, ask you to pause the video, work it yourself, and then check your answer against the solutions that I will go over after that. So the first one we have on this video is exercise 6. Let x be a geometric random variable with p equals 0.65. Compute the following probabilities in decimal form rounded to 4 decimal places. Probability that x equals 4, probability that x is less than or equal to 6, probability that x is less than 3, probability that x is greater than 5, probability that x is greater than or equal to 4, and the probability that 2 is less than or equal to x, which is less than or equal to 4. And then tell me the mean and standard deviation of this distribution. All right, your turn. Press pause now. Okay, so when you have the probability that x equals a number, that's just a PDF. In this case, it's a geometric PDF. You also have to pass it the parameter 0.65 to identify which geometric random variable is. So that's just geometric PDF 0.65, comma 4. And there it is. Round that off, 0.02789. Probability that x is less than or equal to a number, that's just going to be a regular CDF. Okay, and once again, this one's a geometric, so that's a geometric CDF, 0.65, comma 6, and enter. These are screens from a TI 84 calculator or 83 calculator. You find geometric PDF and geometric CDF under distributions, which is second variable, second VARS for distributions, and you just arrow up and down until you find these. Actually, if you'll just arrow up from the arrow up, these are near the bottom of the list, so it kind of cycles, and you can find it. Some of you will have a screen between this where it will ask you to put in the probability of success P, and then it will also ask you for the X value, which is the two numbers here. If you have the older operating system, you just have to remember the order. It's P and then the X for both PDF and CDF. Now, on part C, we want the probability that x is less than 3. Now, remember that for a geometric random variable, the only values of x that actually have any probability are whole numbers, actually natural numbers, 1, 2, 3, 4, 5, and all the natural numbers. So less than 3 really means less than or equal to 2. So that's just a geometric CDF 0.652. So notice those less than or equal to are left probabilities, which is what a CDF computes. But of course, that one was put in 2, not 3. Now we want the probability that x is greater than 5 for part D. Greater than is a right-tailed probability. That's going to be 1 minus the left probability. So it's going to start out with 1 minus, and then you do the CDF. So now let's see. We want to keep the bars from 6 and up. And there are infinitely many of those bars, actually, 6, 7, 8, 9. It goes on forever for every whole natural number from 6 and up. But we're going to get rid of the bars from 1 to 5. So we do that as 1 minus the geometric CDF. Again, 0.65, but we go up to 5 for the part that we want to subtract. So that'll subtract the probabilities corresponding to 1, 2, 3, 4, and 5 for x. And that's pretty small. It's 0.0053. Again, probability that x is greater than or equal to 4. That's going to be a 1 minus, because it's a right tail, the greater than. Okay, and the CDF gives you the left tail. So we do a 1 minus geometric CDF. Now let's think about this a minute. You have to be a little thinking about what we want to, do we include the 4? Which part do we, is the 4 included or not included what we want? Is it included or not included with what we subtract? Well, we want to include the 4, so we want to keep the bars for 4, 5, 6, 7, 8, 9, 10, and so on forever. Which bars do we want to get rid of? Well, just the bars for 1, 2, and 3. 3 being the top one is important. That was the top one we want to get rid of. So that's 1 minus the geometric CDF of 0.653. So that's 0.0429. And when you do a probability between two numbers like this, it's the difference in two CDFs. So if we do Geometric CDF 0.654, that'll do the probability from x going anything less than or equal to 4. So in this case, geometric, it starts at 1 for x, so it's probability for x equals 1, 2, 3, or 4. Well, from that, we want to get rid of some, actually just 1. We want to keep the bars 2, 3, and 4. We want to get rid of that 1, anything below 2, which in this case is only the one at 1. So that's 0.651 geometric CDF, and do those, and you get the difference between those, which is the probability you want, 0.3350. The mean is just is Q, 1 minus 0.65, and the standard deviation is the square root of P times Q. So we get that. Now let me show you up here. So that down there was if you had a TI-84. Basically, the formulas are worked exactly the same way up here for the mean and standard deviation, but the way the CDFs work is a little bit different. The geometric PDF is basically the same. It's geom instead of geomet, but it's either one's short for geometric PDF, so that's the same. But the way the CDFs work a little differently on the TI Inspire, which is what this is. So if on this one, x less than or equal to 6, that's really bars corresponding to x's of 1, 2, 3, 4, 5, and 6, from 1 to 6, including the bars for 1 and 6, the probability of the 1 and the 1 and the 6. So you just give it a lower and an upper, and it gives you all the probabilities of those in between, including those two. So less than 3 would be just for 1 and 2, so you put that. Greater than 5, well, we could start at lower 6, but we'd have to put infinity for an upper. That's not a good thing to try to do. So we can still do this as a 1 minus. So 1 minus geometric CDF from 1 to 4. And this one here is 1, again, 1 minus the geometric CDF. We're going to keep from 4 up, so we want to get rid of from 1 to 3. And this last one's the easiest one, actually. You just give it the 2 and the 4, and it gives you the probability between those, including that. So this is the Inspire is not a true CDF, but it's actually easier to work with for the most part. All right, here's a similar problem, but this time for a binomial distribution. Let x be a binomial random variable with n equals 15 and p equals 0.35. Compute the following probabilities in decimal form rounded to 4 decimal places. So if you can do the last one, I think you should be able to do this one pretty easily too. Okay, find the probability that x equals 7, the probability that x is less than or equal to 5, probability that x is less than 10, probability that x is greater than 12, probability that x is greater than or equal to 6, the probability that x is between 5 and 10 inclusive, and then find the mean and standard deviation. Go ahead and work this one out. Press pause now. All right, so of course, obviously you want to have your calculator out ready to go. With my students, I require them to use a calculator on exams and not use something else like, Excel or anything else on your cell phone or any kind of statistical package. So anyway, let's work this out. So again, when x equals a number, that's going to be a PDF for a probability. So we just want the probability that x equals 7. That's a PDF. And which one? Well, it's a binomial PDF, so it's binom PDF. And the order here is n, p, and the x. And again, many of you are going to have a screen that comes in and it asks you for that. So let's say n or trials. I think it says trials. And you put 15. That's also could have said sample size or number of trials or just n, little n. That's 15. That it's going to, I think it just says p, which is the proportion of successes in the population or the probability of success each and every time we do draw one of these things. And then we want to find what's the probability that that x value is exactly equal to 7. Again, that's a PDF and a 7 here. So the answer is 0.1319. All right, what's the probability that x is less than or equal to 5? Less than or equal to, that's exactly what a CDF does. So that's just binom CDF, 15, 0.355, 0.5643. So a couple things you can do with the newer calculator. Well, even the older one, you can say second enter, and it'll bring up the previous entry, and you can just change the number to, well, just the last number here. Well, they won't work for this one because this is PDF. But going from this one to the next one, you could do that. Okay. The next one's also a CDF, probably that x is less than 10. Since there's nothing between 9 and 10 that gives us any probability, this is really probably that x is less than or equal to 9. So it's binomial CDF 15.35 and 9. By the way, you get binomial CDF by pushing distributions, which is second variables, second VARS key. Distributions is written above that. Then you choose binomial from that list. Binomial CDF, I happen to know, is B. So if you know that, you can just do second B, or alpha B, excuse me, and then that will come up directly in your list, or you can just up and down arrows till you find it. All right, so anyway, that turns out to be 0.9876. Okay, the probability that x is greater than 12. Okay, the way your calculator works, if you have a TI-84, it's a true CDF, which is a left probability. If you want a right probability, which is what we have here, you have to start with 1 minus appropriate left probability. Now let's think about this a minute. We want to keep 13 and up. We want to get rid of 1 to 12, the probabilities that go with those. So that's 1 minus binomial CDF. Again, n is 15, p is 0.35, and then we want to go up to 12. Now look at this. Don't forget this e negative 5. That means 0.4. That means move the decimal place 5 places to the left. 1 will put it there on this side of the 5, and then we got to cross over 4 zeros. So it's 0.4 zeros and then a 5. Well, that rounds off to 0.3 zeros and a 1. Probably that x is greater than or equal to 6. We want to get rid of the, let's see, we want to keep from 6 up, 6 to 15 in this case, keep those probabilities, and we want to get rid of then the probabilities from 1 to 5. So that's 1 minus binomial CDF of 15 minus 0.355. Answer 0.4357. And again, like in the geometric, when you have this setup, the probability that x is between two numbers, the way you do it on a TI-84 is to do the difference of two CDFs. So the binomial CDF from 15.3510 is going to give us all the probabilities up to 10 for x. So x is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. But then we want to subtract or get rid of the probabilities from corresponding to x's going 1 to 4. And so that would be minus the binomial CDF of 15.354. And that is 0.6452. So those same things on the Inspire, the binomial PDF works the same thing as ways this one does. Okay, and you can find these under distributions, statistics, I think, probability distributions, I think. But the way the CDFs work are differently. They're not true CDFs, but they're actually a little easier to work. So the probability of x is less than 5 means x could go from 0 to 5. Remember, on a binomial, the lowest you could go and get something is 0 successes. So that's 0 is a possibility. 0 wasn't a possibility for geometric distributions. So this goes from 0 to 5. That's the bars we keep. This one here goes from 0 to 9. Give it the lower and the upper. Then this one, it's easier. If you greater than 12 would be 13, 14, and 15. So that's 13 for lower, 15 for upper. And this one here, greater than 6, greater than or equal to 6, starts at 6, it goes up to 15. And the last one is the easiest. It's the 5 and the 10 there. And those numbers should agree is what we had here. Now the mean is just n times p, so whichever calculator you do it on, it's basically the same. 15 times 0.35 is 5.25. That's the measure of center, the mean, the average, the expected value. And the square root of n times p times q is the standard deviation. So 15 times 0.35, which is what we just got here for the mean, but then we multiply that by q, 0.65, and then square root the whole thing. We get 1.8473 to 4 decimal places. Well, here's the same thing for hypergeometric, right? Let x be a hypergeometric random variable with capital N is 53, capital M is equals 21, little n equals 8. Compute the following probabilities. Again, give them a decimal form rounded to 4 decimal places. Hopefully you can see those and work them out yourself. Press pause now. Okay, now you're back. It's very similar to the last one. This time, however, there's not a hypergeometric distribution built into the calculator, either the TI-84 or TI-83 or the TI Inspire. So you have to use the function that I told you how to build for the TI Inspire, or the program that I showed you how to put in for the TI-84 or TI-83. It's very important that you get this program in, okay? So see the earlier videos for how to do that. So we run the program, Hypergeometric CDF, and every one of these, we're going to run the program, 6 problems, we'll run it 6 times. Each time it's asking for the population size. That's capital N, but I had to use 2 N's here, so I used the N that was built in, which is unfortunately capital 1 for the sample size, and I picked S for the, I guess, for the something else for the population size, okay? So anyway, the first, but it tells you what here. Total population, that's 53. The number of successes in the population was 21. The sample size is little n, which is 8. And the interval of successes, we go from lower to upper. Well, if you're doing a just at 6, that really should be a PDF, but with the CDF built like this one, you don't really need the PDF. You just use lower and upper the same number. It's just 6. Lower is 6, upper is 6. So this would just be the probability that x equals 6, 0.0304. Now, probability that x is less than 7. Now, this part here, these first 2 screens are the same for all 6 of these problems. It's just what you put in for lower and upper. So for less than or equal to 7, lower is 0, upper is 7. Pretty high, 0.9998. Less than 2, well, that's then lower is 0, upper is 1, 0.0916. Greater than 6, well, that would start at 7 and make its way up to n, which is 8, between 7 and 8, 0.0044. Greater than or equal to 4, that starts at 4 and goes all the way up to the sample size of 8. Can't get more than 8 successes. From 4 to 8, 0.3915. And this one, of course, just from 5 to 7, 0.1484. And the TI Inspire, it uses a function, but it's not a built-in function. It's one we had programmed into it. Call that up, and you can get this. Now, to call the function up once you have it in, you could have a couple options. One, you can type the name of it, HGOPDF, and then parentheses and put the stuff in there, okay? But you can also get there from just doing, I think it's second variables, to get a list of it'll give your programs and functions and things that you already have programmed in. So anyway, this is HGOCDF, and again, I actually did it by first graph building up a PDF, so you can use the PDF for that one. You have to give it, again, in the same order as the other program comes in, big N, big M, little n, little x. But once you have that set up, all these are the same. So the easiest thing to do really is just go back in here, click enter on the one before. It's going to come back, change the numbers. Like here, we want to go from 0 to 1 to get the stuff less than 2. From 7 to 8, this would be the stuff that is greater than 6. And so forth. All right, now let's do some real-world applications now. Basketball player makes 40% of his free throws. Assuming that each free throw are independent, compute the following probabilities in exact percentage form. What's the probability that his first free throw made will be on his third attempt? And what's the probability this first free throw will be made among the first 4 attempts? So what do we have to do? We have to decide what kind of distribution is this, which function or program to pull up on the computer or calculator, what numbers to put in, and how to interpret the output. Well, if you're counting if you're doing this success or failure, basket or not a basket, make the free throw or not, and then you do that until you get your first success, that's exactly what geometric random variable is. So if x is the number of 3 throws until the first success, then x is geometric random variable with p equals 0.4. So what's the probability that his first 3 throw made would be on the 3rd attempt? That's just geometric PDF of 0.43. It's about 14.4%. And the probability his first 3 throw will be among the first 4. That's 0 up to 4. That's a 1 up to 4, excuse me. But it's going to be a geometric CDF, so it's just 0.4, 4. About 87.04%. And I guess those are exact values. Okay, one more for this video. Suppose there's an organization with 60 members, of which 25 are women. A committee of 10 members is randomly selected from the membership. Compute the following probabilities in decimal form, rounded to 4 decimal places. The probability that there are exactly 4 women are chosen on the committee, and the probability of women comprising a majority of the committee. Press pause now. All right, well, what's going on here? We have a finite population size of 60, of which 25 of them are successes. Remember, don't put a value judgment on success. It's just what we're counting. So X's, we're going to count the number of women on the committee. And the committee has 10 members, so it's a sample of size 10. So this is exactly a hypergeometric situation. We're not going to choose the same woman twice for the committee, so it's done without replacement. So the probability that x equals 4 is just going to be, well, it's a PDF, but we can do it from the CDF program. So again, the population size is 60. The number of successes in the population is 25. Sample size is 10. And we will go lower to upper. We're going to go with exactly 4. So it'll be 4 for lower, 4 for upper. That's 0.2723. That's what I got up here. Find the probability that women comprise a majority. Well, what's a majority? It's anything above 50%. 50% of 60 is 50% of the committee. 50% of 10 is 5, so it has to be greater than 5. So that's actually the same thing. The first 2 screens are the same, but for lower you put in 6 and upper you put in 10. And you get 0.1743. This is how you do it on the Inspire. Okay, let's stop there. We'll do another 5 in our last video for this section.